Hi. So we know that MEMS means micro electromechanical systems, and in last few modules we discussed about the mechanical part or the basics of some mechanical formulas or some basics of mechanical concepts which we need to use. And now in this module we will switch to electronics or like more precisely electrostatics part, and then after giving you some basics of electrostatics, we will discuss that how a coupled electromechanical system works. Okay. So while you have a electrical force also, and while you have a mechanical force also acting on a body. So let's go through quickly, and so I will not go into very much details, just a few basic concepts of electrostatics. So most of you are already aware of this part actually in during your 12th standard or some basics undergraduate courses on electrical field or electronics field. Okay. So first we are discussing about the Coulomb's law. I am not going to write down the law, but what you can see here is I will just brush up the formulas once. So let's say this is two charges Q1 and Q2, right? I am not writing any sign for them, and they are, let's say, apart by a distance r. Then what is the magnitude of this force, like the electric field or force on? So now what is the force that is exerting one body on charge on another? Okay, that is 1 by 4 pi epsilon naught into Q1 Q2 by r square, and this is you are already aware of, right? And note here we have mentioned that the magnitude of the force. Okay, I am not writing any direction, just for simplicity. And then this is the force. Now what is the field? Force per unit charge. So field, let's say electric field on one charge due to the another, let's say on Q2, because of the Q1 charge is 1 by 4 pi epsilon naught into Q1 by r square, because force by Q2, right? So this is the electric field. Or in general we can write for a charge Q 1 by 4 pi epsilon naught into Q by r square. Let us assume the charges are Q. Now this is also you are aware of that work done is equal to, or energy is equal to, force into displacement, right? So here if I have a charge Q at this point, right, let us say it is plus Q, and then we have electric field at some point which is at a distance r is equal to Q by r square into the constants are there 4 pi epsilon naught. Okay. Now at various different distances, like if this r changes, then this electric field also changes, right? So while we are calculating work done to bring a charge from infinity to at some point r, okay. So let's say we are bringing another charge, like let's say 1 coulomb of charge from infinity to some point at r. So what is the electric field at r is equal to Q by 4 pi epsilon naught r square. What is the electric field at infinity? Is equal to 0. Correct? We can calculate it as r square. So in a denominator there will be infinity, so it will be 0. Okay. To calculate the total work done, what we need to do? We need to integrate it. So W is equal to E dot dr, right, where r is equal to infinity to some r. Now the point is, let's say if we consider a charge of q, which like another charge, if it is 1 coulomb charge, then it is E dot dr. If it is like some charge of q prime, then I need to write q prime E dr, right. Now this you have already done. If you put the electric field, then let's assume this is 1 coulomb charge only, then it is q by 4 pi epsilon naught r square dr into infinity to r, and then if you do the integration, you will get w is equal to minus 1 by 4 pi epsilon naught to q by r, and this is called potential, right, electric potential due to the charge q at a distance r. We will call it V, electric potential V. Now another important concept you need to understand is this electric field or potential, whatever we are calculating, is for open space or like free space, right, where there is no material. But if we have a material like some metal or some dielectric or any kind of material, then depending on the material properties, there will be some kind of polarization. Polarization means that the electrons and protons inside that material will arrange themselves by some kind of arrangement by some due to the external electric field, and because of that the electric field inside the material will not be same as the external electric field. Okay, so for dielectric material, if we consider the electric field inside is d, some displacement field, then it comes as epsilon into the electric field outside or the external applied electric field, that is E. Okay, so and this epsilon is equals to epsilon r into epsilon naught. So and this epsilon r is equals to relative permittivity, relative dielectric constant. Okay, so this is just you need to remember that while we are applying some electric field, if we have a specific material, then the field inside the material may not be same as in the air or in the free space. Okay, now we will discuss another very important concept of electrostatics, that is Gauss law. Let's assume we have some charge distribution, and because of that we have this material, and there the electric field at any surface point is E, and this surface is, let's say, ds. Okay, so this surface is ds and electric field this point is E. Now this surface is also, you know that the surface is also a vector, right. So this has its direction perpendicular to the surface. Now according to the Gauss law, surface integral is E dot ds is equals to the charge enclosed q enclosed divided by epsilon. So as I was saying that at every point in this or every small elemental area we have an electric field, and that electric field, if we take a dot product of that, like the surface vector and the electric field, then E dot ds is the like flux through that small area, and then if we integrate over the flux, then we get the charge enclosed divided by epsilon. So this is Gauss law. Again, see that the charge enclosed is equivalent to equals to we can also write that Q enclosed is what? The total charge enclosed, and if the charge density is rho, then the Q enclosed is the integration over rho dV, right, where dV is the small volume element. So here we can write 1 by epsilon is equal to into rho dV. This equation of Gauss law is like basics of electrostatics, so I am not going into the details of that, but we can use this expression while whenever it will be required. Okay. And another thing is, from the vector calculus we can write this expression in another this formula in another expression, right, and that is divergence of E is equals to rho by epsilon naught for the free space. So this also comes from electrostatics or vector calculus. Now we will take a specific case of surface charge distribution. Okay. So surface charge distribution, let us say I assume an infinitesimally infinitely large surface, and where the charge density is sigma. So surface charge density is sigma. That means that sigma is equal to Q by A, right, where A is the area. Okay. And then I assume a Gaussian pillbox. So what is a Gaussian pillbox? Gaussian pillbox is this kind of parallelepiped you can assume, and this is going, let us say, into the surface, and coming out of the surface. Okay. Okay. So this parallel pipe is ultimately enclosing some amount of surface charge. Now we will use Gauss law. According to Gauss law, we know that integration over surface integration over E dot ds is equal to Q by epsilon naught, where Q is the enclosed charge. Now let us assume that here in this point the electric field is E, and then for both the sides it will be the same constant electric field. Why? Because this is infinitely large surface charge distribution. So even if we move in the xy direction, where this is, let us say, x and this is, let us say, y direction, then it does not change the distribution with respect to any of those points, right. In a plane it will be the same electric field. So what we can write, this E can be constant. So now according to this Gaussian pillbox, let us say this Gaussian pillbox have a area of A. Okay. Let us say the area is A, cross sectional area. Now we can write that the total flux out of this area is E into A into 2. Why? Because there will be flux out of this, the top side, and also from the bottom side, correct. So we get E into A, that is 2, A into 2 is equal to Q by epsilon naught. Now what is Q? Q is equal to charge enclosed by this pillbox, and this pillbox has an area of A. So Q is equal to sigma into A, because sigma is my charge density, so into area is my total charge, by epsilon naught. So E I can write as sigma by 2 epsilon naught, right, and if we add the vector sign, then E vector is equal to sigma by 2 epsilon naught n cap, where n cap is the surface normal vector. Okay. Now let us consider two parallel plates, okay, separated by a distance d, and two plates are having charge plus q and minus q. Okay. So let us consider two parallel plates, and they are separated by a distance d, and each of the plate is having some charge q. One side it is positive plus q and another side it is minus q. Now what I need to do is calculate the capacitance of this arrangement. So if we consider, as we just now discussed, that for a infinitely long large plate we can consider we calculated that the electric field at any point or at any distance is electric field is equal to E equals to sigma by 2 epsilon naught n cap, right. Now here for plus q, let us say this is the same then we can consider that the charge distribution here it is plus sigma and here it is minus sigma, okay. Now because of the plate A, let us say plate A and plate B, I name the two plates. Because of the plate A, the electric field at any point is in between is sigma by 2 epsilon naught n cap, and that is directing in this way, right, because of the plus q charge. Whereas for the minus q also it is of the same magnitude, but direction is same because this is negative, so the n cap also will be directing towards the surface, right. So the equivalent electric field inside this will be E equals to sigma by 2 epsilon naught into 2, because both the fields will add up, correct. So EAB, so that is sigma by epsilon naught. See, these two plates are in parallel and the field inside the plate is uniform electric field, okay. Now as it is uniform electric field, if the potential generated in between them, and the potential difference in between them is V, then we can write that E equals to V by D, right. Anyway, you know that E equals to any electric field we can write as E equals to dVdr, right, and some vector will come, let us say r cap, and you can write that the first derivative of the distance, first derivative of the potential with respect to the distance is the electric field, and here the electric field is anyway uniform, so you can directly write that electric field is equal to V by D. And another thing is that sigma is equal to Q by A, right, like mod of sigma is equal to mod of Q by A. So if we put this expressions in the electric field term, then we get that E equals to V by D is equals to 1 by epsilon naught is equal to Q by A, or Q is equal to epsilon naught A by D into V. Now this epsilon naught A by D, this term is known as capacitance. C, capacitance C, and if we put this C, then we will get that Q equals to C into V, where C is equal to epsilon naught A by D. So this is the expression for the parallel plate capacitor, and then if we have a see here in between the parallel plates, if we have any dielectric material of let us say some dielectric constant epsilon, then this expression will come as C equals to epsilon A by D, okay. So as I was saying, because while you have a dielectric constant, or while you have a dielectric material, then in that case the electric field E will not be same, rather it will be epsilon into E, and then in that case it will be replaced by epsilon. Epsilon naught will be replaced by epsilon, where epsilon is the free space dielectric constant or free space permittivity into relative permittivity epsilon r. So this parallel plate capacitor equation we will need in this course very frequently. So now we will discuss little more about the electrostatics which may be required for the for this particular course. Okay. So as I was saying that electric field is equal to first derivative of the potential, right, dVdr. Now if we have a three-dimensional distribution of the potential like this, that at every point xyz the potential V is different, like it is a function of xyz, then in general form we can write that E equals to minus of grad V, right, where V is the scalar, but this is the partial derivative like del del x plus del del y plus del del z, and with respect to its like direction, like I cap into del del x. So these things you already know from the vector calculus. J cap del del y plus k cap del del z, and then you have potential which is a function of x, y, z. So this is one expression which you may require, or while you are solving any problem where you do not have a very simple case like point charges, rather you have a distribution, then calculating the electric field etc., you need to apply actually this general equation. Okay. And in this equation, if we E equal to grad V, in this equation if we apply another first derivative, right, or another differential function and the delta function, then we will get divergence of E is equals to minus of del square V, right, and divergence of E equals to, earlier on itself we have seen from Gauss's law, that is equal to rho by epsilon, correct. Now del square V or Laplacian of V is equals to minus rho by epsilon, and this is known as Poisson equation. Okay. And if we have a charge distribution, let us take a free space where if you have a free space where rho is equal to 0, then we have Laplacian of V is equals to 0, and this is called Laplace's equation. So this is Poisson equation, and this is Laplace equation. Now the point of discussing this is, see, one thing is that you know the potential. If the potential is given, then from the potential you can calculate the electric field using this E equal to minus grad V. If you do not know the potential, if you are given the charge distribution, that is you know the rho, then you can calculate the potential from the Poisson equation, right. And if you do not have any charge distribution, but if you are given just a boundary condition, like the potential is mentioned at some point, and but the charge distribution is not known, right. So in that case also you can calculate the potential field, like what is the potential or V x y z at different point using this Laplace equation, and from that you can again use E equal to minus grad V to calculate the electric field at different points, right. So this is some basics of electric field like electrostatics, and now we will move on to the next part. We will now discuss one more concept on the parallel plate capacitor, that is, let us say this is the capacitor as I was discussing, and then you have a charge of plus Q and minus Q on this capacitor, and so the area of both the plate is A and the distance between them is D, right. And then if these plates are connected to a battery V, like the potential difference and the potential difference between the plates is V, right. So then what we have seen that Q equals to CV, where C equals to epsilon naught A by D, right. Now if this is Q, then what is the current? Current I equals to, you know, dq dt, right, time derivative of the charge stored or charge flown, and then we have C into dV dt, because C or the capacitance is constant and it is based on the geometry and the material, right, of the parallel plate system. Now current I equal to C dV dt. What is power? Power is equal to, you know, voltage into current, that is power at any point t is equals to I into V, that is I is current and V is voltage. Now this V and this I is not constant, because as the charge will flow, the potential will also build up slowly. Let us say the capacitor initially it was not charged, so capacitor was at 0 charge, so the potential was also 0. Now as we connected the battery, because of the battery, now it tries to starts to store the charges, and because of that the potential starts from 0 and it build up till V. What is the potential difference of the, like the potential that the battery can provide. Now this is the power. So at any point t, the power, let us say it is a function of time, I is also a function of time and potential is also a function of time. Then what is the energy? Energy stored at some time d is energy stored till some point t is I into V into dt, or integration over 0 to t, right, and that is C dV dt into V into dt from 0 to t, right, and then we have, let us say this t is like very large, so the capacitor has gone up to the voltage of the battery, right. See, we can take it out, and V dV, and V dV, this V is from 0 potential to the battery voltage, and that is capital V. So then if you integrate it, then we get half of CV square, right. So the energy stored in a capacitor while it is charged to the potential V is half CV square.